Thank you very much for the nice introduction, and thanks to the organizer for inviting me. It's a pleasure and honor to be here, especially when I read the name of the other speakers. I was amazed. So today I would like to share with you some of the results and work that we have been doing in the latest, let's say, 5-6 years, together with some PhD students of mine. Now some of them, one of them is my colleague, and with some postdoctoral researcher that now move and have a position actually here in UK. So what motivated this research was the challenge that large-scale system present. So we developed methods to address multi-agent cooperative decision-making. And a main challenge was that of energy system. Our society, as you know, is facing for sustainability issue, climate changes issues, this big challenge, and we decided to focus on that as a motivation. So multi-agent systems are pervasive in our society. You can see them in social network, robotic network, transportation systems, and in particular in energy system. This is just a representative picture of what's a microgrid, a smart grid. And for energy system, as I was telling you, there is this target to which more than 70 countries agree on reaching net zero by 2050. Which means that global greenhouse gas emission would need to be reduced already of 45% by 2030 to reach this balance between what is produced in terms of greenhouse gas emissions and what is absorbed by the atmosphere, ocean, and forest. And among the sources of greenhouse gas emission, there is the energy sector, which is actually contributing nowadays with three-quarters of greenhouse gas emissions. So it's becoming mandatory to try to replace traditional polluting fossil fuel power with energy from renewable sources, which, however, poses, as you can guess, challenges, because wind and solar are intermittent energy sources which we cannot control. So this can cause imbalance between generation and power in the grid, which needs support. In general, in order to reach this target, you can think about two main challenges. One is that we should use current energy resources more efficiently, trying to consume less and to use equipment at the best efficiency level. And on the other hand, support the penetration of renewables, for example, by providing balancing services to the grid, in trying to recover this from possible imbalance due to renewable. In my presentation, in the work that I've been doing, we are focusing on decision-making problems that admit a formulation in terms of an optimization program, a mathematical program where you have decision variables, and these decision variables are subject to constraints, and they should be set in order to minimize a cost function. If you think about control problems, you can think about finite horizon control problems, which are key to MPC technique. So in this talk, I will focus on this goal, so optimize the performance of a system, which is a large-scale system, composed of subsystems, which are called agents because they have computation and communication capability, so they can communicate with each other and compute and contribute to compute the solution for optimizing the performance of the overall system, and in this respect they are cooperative. So the characteristics that cause challenges in addressing these issues of performance optimization for multi-agent cooperative systems is that typically the system, as in the example that I show you, are large scale. There are many interacting components, many agents. Each agent is different from the other because it might have different goals. and different physical and technological constraints. And then it's often the case that you have uncertainty that enters the system. And often the decision variables are both continuous and discrete. And as you might guess, when you have discrete decision, in principle, you should exhaustively search among all possible combinations, and then you have combinatorial complexity. So the challenges that we try to address by formulating a distributed database optimization framework were mainly these three. On one end, the computation. You have problems that are of too large size, and we try to decompose it in smaller size problems. Preserve privacy, even if the scale is small. Agents are willing to contribute to the overall good for the overall system, but at the same time, they might be not willing to share their local private information. If you think about energy system, I might be willing to support the grid in balancing servicing by shifting my load request, but at the same time, I wouldn't like the other to know when I'm having my load request. So my personal profile when I'm at home, when I do laundry or whatever. And at the same time, another challenge is represented by uncertainty, which often is known just through data. So we went for this solution, which is basically trying to decompose the problem in parallel smaller optimization problems, which are local to each agent, which doesn't need to share its local information to the other. And we try to account for uncertainty using data. You see in a while. So why is this distributed solution might have advantage? Because it's a scalable methodology. So you have agents that make their computation in parallel and communicate just with the neighbor one. It's resilient to communication failure to a certain extent, in the sense that you'll see that the communication network is described through coefficient that might also be zero, meaning no communication, as long as you preserve some connectivity. And it's also characterized the distributed structure. It's also embedding preservation of privacy, because when agents solve their problem, they exploit their local information and they don't share it with the other. They just share the solution, their tentative solution. And you have a number of applications of distributed system, like the one that I mentioned you before, and many in energy system. So what I'm going to do next is to drive you through this trip. We start from deterministic decision coupled problems, which are motivated by an application. We'll set up the stage, the problem characterization. I will propose one algorithm, distributed proximal algorithm, make some analysis, show some analysis result, and then I will move to uncertain case, setting up the problem, proposing the database approach, and this distributed implementation. Then we'll move to another class of problems, which are named as constraint-coupled problem. We'll see how we can extend this proximal algorithm by moving to a dual. And then I will show also some results on the discrete case in order to address this combinatorial issue, when you have to take also discrete decision. And finally, I will draw some conclusions. So let's start with this motivating example. Assume that you have let's say, campus in the university, a building district, and we are addressing here a cooling problem. So we are in summer. Every building has its own chiller plant, which means a plant that converts electrical energy in cooling energy. And they share a sort of, let's say, battery, a thermal storage device, which is represented by a shared cooling network. And the goal here is to determine the use of a storage system plus the setting of its own temperature set point in order to minimize the cost of electrical energy consumption for the overall district. So a chiller plant is characterized by a coefficient of performance, which is this curve. Given a certain cooling energy, you have provided you have a value here, The higher is the value, the smaller is the amount of energy, electrical energy, that you need to produce such a cooling energy. So you can see that different devices are characterized by different curves, and I will say that this one that can provide a higher value of cooling energy is a large one. Then you have an intermediate one, and then you have a smaller one. You would like to operate these devices at the highest efficiency point so that they consume less, basically. So as for what concerns the building, you must take into account when you address this cooling problem that there is an exchange of energy between walls and zone. According to a building thermal dynamics, there is energy due to the fact that there are people occupying the building, there is a thermal inertia of the zone itself, and then other internal energy contribution which are related, for example, to radiation through windows. I'm not showing the equation, just to mention the kind of aspects that you need to take into account. And the thermal storage can be modeled as a battery, as I said, where you have energy stored in time slot k plus 1, which is the previous energy with some energy loss coefficient alpha, a coefficient between 0 and 1, minus because if you discharge the storage is actually accounted for as a positive quantity. If you charge it as a negative quantity, the sum of the contribution that comes from all the different buildings. And then, as you can imagine, you can formalize the problem that I mentioned you before as an optimization problem where you minimize the sum of the cost of a similar electrical energy consumption subject to all the constraints related to the devices that you are using, storage dynamic, storage limit, Siller limit, comfort constraints, plus the equation of balance of the energy, so the request of cooling energy to the chillers, it's actually the building energy request minus the one that is provided by the storage system. So I didn't write the equation, but I think it's easy to guess that at the very end you are going to have a problem of this form. You are minimizing the sum of the cost function, one per building, which depends on your decision variable, which means the exchange with the thermal storage plus the set point in all the buildings and the zone of the buildings, subject to constraints that are the intersection of the constraints that are applied locally to each building. So this kind of problem is called a decision couple problem because the coupling is due to the shared decision variables. If you would have a decision variable per building, which represents here an agent, this would be separable. So a decision couple problem in this form is characterized through local objective, local constraints of each agent, and the coupling decision variable. How can you solve such a problem in a distributed way? So the proposed distributed algorithm that it's one in the literature, the one that we proposed is based on this idea. So locally to each agent, at each step of this iterative procedure where each agent proposes a candidate solution and then they have to agree according to a consensus scheme on the common one. Each agent has to minimizes a cost function, which is its own cost function subject to its own constraint, plus an additional term, and this term is actually not working. This additional term, it's related to an information vector, which is constructed based on the information of the neighbor of its agent. It's basically the term that tries to impose the consensus. So each agent receives from the neighboring one their tentative solution, and then it uses this information to try to set up its proposed solution in such a way so as to minimize its own performance and also get consensus with the other. Okay. So after this step, what's going to happen is that each agent, here I'm considering agent I, is broadcasting to the neighbor its tentative solution, receive from its neighbor their tentative solution, and then update this zeta I based on the information received and keep going through this loop. So now what we need to specify is the information vector and this proxy term that try to penalize this agreement. Both of them, they change throughout iteration, and zeta I, this tentative candidate solution, is actually taken as the average of all the solution by the neighbors and the agent itself through some coefficient which may vary along iteration. Why am I allowing this coefficient to change throughout the iteration? This is to account for possible failure of the link, of the communication link. So if this coefficient would be 0, it would mean that there is no link in place. And also it allows to model the graph that represents the network communication topology. As for the term that penalizes disagreement, it's simply the square norm of the difference between the candidate solution of agent I and the average of its neighbor. There is a coefficient here which varies in time, this CK, and the idea is that the CK should trade off between optimality, because if this penalization term were not there, the agent would optimize its own performance index based on its local constraints. Okay, so it's compromising between optimality and the disagreement with the other. So this CK must be chosen appropriately decaying towards 0 in such a way that in the long run consensus is enforced, but it shouldn't do it too fast because otherwise you lose optimality. This is the intuition. And now I may wonder, and this was the goal of our work, what's going to happen in the long run? Does this algorithm converge? And is the solution to which the agent converge the same one that I would get by solving the original problem centrally? So bringing all the information to a central unit, the central unit knows everything and they solve the problem if it were ever possible to do it, because it might be a large scale. And the answer is yes, but under some appropriate regularity assumption. In particular, you need, not surprisingly, convexity, because convex means well-behaved, means that a minimum exists, there is just one global minimum. And then compactness, compactness of xi, Lipschitz continuity at the very end of the function. And as for the proxy term, as I told you, this CK must decrease, but not too fast. So if you sum it up, CK blows up to infinity, but its square is converging. So you must think, for example, of the harmonic series, which makes the job 1 over k plus 1, or alpha divided by k plus 1. This is not enough, because you need the information that is shared among the neighboring agents to be appropriately mixing up, and this is guaranteed by imposing that the weights are lower bounded, so that the non-zero one are lower bounded, so that the information is mixing at a non-diminishing rate, and then they have a property that the matrix that is built out of them is doubly stochastic, so both row and column sum to 1. So that the agents influence each other equally in the long run, and you can enforce consensus. You need also connectivity of a network, because if it were separated into subparts, there is no way that information is spread around and you get consensus, which, however, is a connectivity in the long run. you need to guarantee that any pair of agents communicate infinitely often, and then there is a bounded time that elapses between two successive communication time steps. So for example, in this network, if you have a gossip communication pairwise like that, you get this network connectivity assumption to hold true, because everybody is connected with everybody infinitely often and with a time interval which is equal to 2. So under this structural network assumption, you can actually prove that this proximal algorithm converges to a minimizer of a centralized problem, so that you get asymptotically agreement and also optimality. The rate of convergence is actually dictated by CK and is low enough to trade between agreement and optimality. So there are other approaches in the literature, and the most famous one are the ones related to the gradient subgradient methods. So in the gradient algorithm, you have that each agent is considering its own constraint set, its own cost function, and moving one step of projected gradient. So basically the standard gradient step in the direction where its function is decreasing, but projecting on the constraint set. And using this zeta, which is the average, every time to update its own tentative solution, so as to enforce this consensus. They have similar property of convergence. The advantage of proximal algorithm is that you don't need differentiability, so you don't need the gradient to exist. Actually, there is a version of a subgradient algorithm which generalizes the gradient. But here, if you think about this problem, is actually you can give it to any solver which provides you the solution without any explicit computation of gradient and subgradient. And at the very end, in the non-differentiable case, you can have smoother behavior throughout iteration than in the subgradient case, where given that the subgradient is not unique, otherwise you have differentiability, you can choose one step from the other, a very different one, and get this strange, oscillating behavior. But the rate of convergence is very similar because it's dictated by the CK coefficients. So now let's go back to our example and consider, just for ease of interpretation, the case of just 3 buildings. 3 buildings that are characterized by 3 floors with 3 different temperature set points that you can set up and assume a gossip kind of communication, so they can communicate in pairs alternatively. So if you apply this proximal algorithm at the very end at consensus, you're going to have, this is just for one building, to show the result, representative result. You're going to have the 3 different temperature set point profiles, with one of the intermediate zone, the floor, which is the lowest one, because in this way, since we model the exchange and the thermal inertia, the intermediate floor is acting like a sort of thermal storage, which drains heat of the other zone through the floor or the ceiling. So this is the way you can interpret the result. And if you look at the storage usage, at the very beginning, iteration 1, when a consensus is not really enforced, because CK is high, you get, from the perspective of the middle Siller building, that it's acting in a sort of egoistic way, taking advantage with this blue curve, draining energy from the storage. Positive value represent energy which is drawn from the storage. You can read it them there. And make the other Siller plant put energy in the storage. But if you make this run at convergence, you see what you were expecting, that the largest Siller plant is going to produce energy to charge the storage system. The smaller one, it's actually draining energy, and the middle one is doing most of the time getting energy, but sometimes also putting energy in the storage system. In this way, compared to the case in which you provide a fixed fraction of the storage to every building, in the case you're going to get just one, the medium sealer is operating at high coefficient of operation, at high efficiency. If they share their actuation system, the sealer plant, all sealers are actually operating at high efficiency, and then you get the gain. So sharing, it's good for the society. Okay, yeah, this is the message that you get. But now if you think about what I've been talking about, you may wonder, okay, you give results, but these results refer to some condition where the building operates with a certain occupancy, with a certain radiation, with a certain temperature of the site environment. These are the nominal disturbances. But if you look at reality day by day, it's very much different. If you neglect uncertainty, the risk is that you get a solution that, when applied to reality, it's unfeasible. So this is a problem. So in our research, when we started addressing the case in which you have uncertainty, this uncertainty is modeled here through this delta parameter that belongs to a capital delta set, and it's affecting the local constraints in this decision-coupled problem. So it's an uncertain parameter. We assume this stochastic setup where our hypothesis is that we consider stationary condition where this delta is drawn from an underlying unknown probability distribution with support on a capital delta set. So if you were to solve the problem in this way, by considering all admissible value for the uncertainty, you are going to get a robust solution, which might be conservative, first of all, doesn't account for the probability distribution so that it's cautious with respect to even very unlikely events, delta instances. And at the same time, it might be the case that you don't know capital delta. You just see data. Okay. So the intuitive idea is to apply this that is known in the literature as the scenario approach, where since you have data, which are instances of delta, you just replace the capital delta set with the samples that you have available. So here, as you can see, I'm not anymore considering all delta, but the delta in this set S of sample points. And in some cases, this is very restricted assumption. You can think about scenarios that are shared among all the agents. So all agents know the same uncertainty realization, but in more realistic cases, each one has its own uncertainty realization. So I'm going to talk next of the two cases, common data set and different data set local to each agent. So in order to preserve privacy, this data might be private data. I would like to apply a distributed approach where these data are not shared, communicated with the other. But let's get started with the first case, the easy one, the common data set case, where we have to solve this problem. This problem has the same issue as I mentioned you before. You might have a large number of agents, and possibly they don't want to share the Fi function and the Xi function. However, they possess the same uncertainty realization. So you can simply apply the algorithm that I showed you before by replacing the intersection of over the samples of Xi delta in place of what I call the Xi local delta set. Run the algorithm to convergence. We know that this is going to be the solution of a centralized problem. And then the natural question that comes out is this solution going to be feasible for the robust program? And does this feasibility is going to depend on the instance, the number, the samples that the agent had available? The theory that was developed since 2006, this is the first paper, the so-called scenario approach, helped us to give an answer to this question, providing not robust but probabilistic guarantees. You cannot expect that by seeing some instances you're going to be robust over the delta set, but if a number of instances is large enough, you can expect instead to have a violation of the feasibility condition, which is small. Here it's represented by this epsilon quantity. And the statement on feasibility, probabilistic feasibility, will depend on the multi-sample S that you had available, because you might be very unlucky to get the same sample extracted, so you have to put some confidence in your result, and this is given by this beta. And the epsilon violation depends on beta and the cardinality of the S set plus the dimensionality of the problem through this formula. This is actually a conservative one, but just to give you an idea. So confidence is free in the sense that you see that the logarithm of 1 over beta, I can push beta to be very close to 0 without paying too much in terms of violation epsilon. While what is costly, it's the number of data, in the sense that if you don't have a large number of data, enough data, you're going to get a large value for epsilon. Epsilon also scales as the complexity of the problem that you are going to address, which is a complex problem with the decision variable. So the more are the decision variable, the more the problem is complex, the higher is the violation. This is the message. But now, what's going to happen if instead we consider that each agent has its own set of uncertainty instances? You can still apply the proximal algorithm and get a distributed implementation of this scenario problem. You just need to replace, consider that your local uncertainty set is the intersection over the local samples of the uncertainty set that you get for each sample. You still have a convergence to a solution, which is a solution of this centralized problem. But now the same question arises. And now you could, we went through an approach that, as I will show you, provide better performances than using straightforward the scenario approach for each local problem. And this goes through providing feasibility guarantees at the level of a single agent through an a posteriori result. So this result was worked out by the group still of Marco Campi, involving also Simone Garatti and Federico Ramponi, and originally was in a CDC paper. So there is a probabilistic feasibility that holds locally with a certain violation, which depends on the same parameter as before, but the local one, except for DI, which is not the D, but is a number of support sample, the number of constraints that you should consider for identify the solution. Here it's a graphical representation. This number of sample depends actually on the SI set. Here it's an instance where the solution, which is this red point, has a support constraint, a green one and a blue one, belonging to different agents. So the number of support constraints is 1 and 1 for the two agents. In this other case, instead, the solution is supported by 2 constraints by agent 2 and 0 of agent 1. So you know about this number once you find the solution, and in this respect is an a posteriori result. But we would like to have an a priori result. How we can convert it? First, we need a result that holds for the multi-agent, but this we can exploit the sub-additivity of the probability by upper bounding the probability of not being feasible with the sum of this epsilon. And then, for getting an a priori result, we can follow two paths. either use a conservative bound because we know that the number of support constraints is smaller or equal than the number of decision variables, so we could do it, we could use this conservative bound for each support set at the level of each agent, or we could consider that the sum of these support constraints of this number must be smaller or equal than D because we are solving globally a problem with dimensionality D. And then in order to get a, less conservative approximation of epsilon, we can solve this optimization problem. So maximize this sum, but subject to a constraint that not every DI is D, but the sum is smaller or equal than D. And here is what we get. In the case of common scenarios, the epsilon probability of violation doesn't depend on the number of agents, it's constant. If we were to consider the conservative bound, it will scale like the number of agents linearly. And here is what we get by this optimal solution, which is close to the case of common scenarios and doesn't grow too much with the number of agents. There are other approaches in the literature that address this uncertainty present in the problem, and you get an interesting, almost sure convergent result that was proven in this paper by Lee and Nedich in 2013. But this requires to sample constraints infinitely many times, which means that you should know the mechanism underlying this uncertainty, basically the probability and the support of the probability. Our result is weaker because we are not proving almost sure convergence, but just probabilistic feasibility and probability. But we use a finite number of samples, so it's closer to the actual data-based solution where you collect historical data, and based on the number of historical data, if you are large enough, you get a certain epsilon of violation. Now, for the time being, I talk about this class of problems, but there is another interesting class of problems where actually each agent has its own set of decision variables, its own cost function, its own local constraints, and there is coupling related to a global constraints. This is the case when agents share a resource which impose a budget. So you have a local objective, local decision, but the coupling constraints that create the problem in solving the overall optimization, and this is constraint coupled problem. What was the trick here? The idea here is that if you exploit duality, it means that you get rid of a complicating constraint by softening it and bringing it to a cost function, weighting it by a lambda penalization coefficient, which must be positive to encourage solution where the sum is negative. You can introduce local dual function, which are, as you can see here, you are supposed to minimize a sum with respect to xi, but since here it's an additive cost, you can write it like the sum of this phi I. You get the problem, the dual problem, that allow you to, in case of strong duality, to correctly estimate the value of the cost and possibly recover the primal solution of interest xi, which has the same structure of a decision-coupled problem. It's a decision-coupled problem where you have the same local constraints for each agent, lambda larger or equal than 0, the sum of cost function, maximization instead of minimization, but these phi I are concave, so if you write it like minimization of the opposite, it's the convex problem that we addressed before. So by noticing this fact, we were able to develop another algorithm which actually compute the dual lambda by proximal minimization, distributed proximal minimization. So here are the same steps as I showed you before, but applied to determine the lambda. And then given the lambda, you can recover the primal solution. Actually, the solution computed like that by minimizing by the local dual function minimization are not feasible for the coupling constraints, because by dualizing you soften the coupling constraints. But there is a recovery procedure that was introduced by Shor long ago, which can be proven to provide an estimate of the primal, which actually converge to the minimizer of a centralized problem under structural and network assumptions that are basically identical to the one that I showed you before. You can also extend this probabilistic result with distributed implementation of a scenario approach, also in this case. And then we try to apply it in the case of building district energy management, because you can rephrase it also as a constraint coupled problem. Here I'm simplifying a bit. The zone temperature set point are given, and I'm just optimizing the exchange with the storage system. I want to impose feasibility with a certain probability, and I actually can do it. Here is an instance of a problem with 10 buildings, different cellular size, 3 small, 2 medium, and 5 big. Stochastic cooling energy request a shape like that, and at the end, if you look at the shape, you're going to get a similar result than before. So the bigger cellars are putting energy in the storage. The smaller one are drawing energy most of the time. The middle one are intermediate. Okay. So now, if you're still alive, we move to the discrete case. In the discrete case, we were able to work out result, but restricting our attention to constraint coupled problems, which are linear. So to what are called multi-agent mixed integer linear program, so multi-agent MILs. What's the structure of this problem? You have a cost function which, being linear, is separable. M decision variable, 1 per agent, a coupling constraints and the local constraints, and the local constraint is a mixed integer polyhedral constraint. Just to get a pictorial view, you can imagine that you have both discrete and continuous variable. They are confined in a polyhedral, but the discrete one are actually discrete. So it's actually the polyhedral constraint set, it's actually composed by these lines. If it were both discrete, you'd have points within that polyhedral set. And this makes the problem complicated and make the combinatorial complexity issue arise. So in this case, since you have this constraint couple problem structure, we can think about applying the same duality-based approach, but now the recovery procedure doesn't work anymore, because when you build this average, the average is not guaranteed to satisfy the integrality constraint. It's not an integer valued, it doesn't satisfy the constraint of being in this mixed polyhedral set. The idea is then to try to give up a bit with optimality to find at least a feasible solution. This is an issue in practice for large-scale MLPs. And then to be able to quantify the quality of the solution and the degradation. So in the literature, if you look, there are some problem-specific approaches in specifically structured MLPs, but there is a quite general approach based on duality that was developed by Vujanic and co-authors in 2016. So the idea of this approach is to try to reduce the budget, tighten the coupling constraints of some amount in such a way so as to enforce that the actual budget is satisfied. This is quite intuitive, and in fact they were able to show that there exists such a rho tilde value, such that if you tighten the constraint, you solve the problem, you are going to get a solution which satisfies the original budget constraint. And you can do it by recovering it from the dual optimal solution associated with this tightening. So we extended this approach by making it less conservative, because as you can imagine, the more you tighten, the more you basically constrain the problem, and you get a suboptimal solution, which is related to an infinity norm. There is an expression in the paper of the tightening vector. And we try to not reduce the budget of this worst case amount, but to try to do it on our way through an adaptive approach while exploring candidate solution. And this work effectively. You can show that your tightening it's smaller or equal than the worst case tightening. A key property of this approach that you get feasibility in a finite number of iterations, which is very interesting if you think about, at some point you need to decide what action to apply in an MPC rolling horizon fashion. And then performance can be shown in the similarly to what is done in this original paper, and is typically better because the tightening is less conservative. But still, in some cases, you have to tighten so much that you get an unfeasible problem to be solved in the first place. So we thought of using another approach, which is inspired by control, in the sense by when you control, you have to bring a quantity to zero, impose that is zero, you insert an integral action. So driven by this simple consideration, what we did was the following. We start with a row, which is small, 0. You solve a dual, you compute the optimal, lambda, recover the solution. If it's satisfying the coupling constraint, then you're done. Otherwise, you determine the violation of the constraint, how much is violated, and you add it. Saturating, because it doesn't make sense that it overcomes the most conservative rho tilde value that was computed by Vujanic, and you keep going. Why this is going to be less conservative? Because when you solve the dual with a certain rho, you are trying anyhow to, enforce the coupling constraints. So this violation is actually small. And even if you integrate, you get to a lower value than the rho tilde, and then the rho that was computed by the adaptive approach developed in one of our earlier work. So now I'm showing some simulation results. I'm showing this result on an example that can be seen as how can we support the grid in balancing services, because the grid, in order to find some support from, let's say, prosumers, users, can do it in two ways, through an explicit or an implicit demand response action. An implicit one is when, based on the cost tariff is driving the users to request energy when there is a lot of production, and less when there is instead little production. Or explicit, if you make a contract with an aggregator that put together, for example, a set of prosumers with generators, with loads that make a service to the grid. So in this case, I'm considering implicit demand response in the sense that I have a fleet of electric vehicles. They need to charge, but they can both charge and discharge or do nothing. And by doing this, driven by the cost of electric energy, they shape their demand according to what is the need of the grid, but indirectly. So we consider a fleet of 250 electric vehicles that have to decide their charging schedule in 8 hours horizon, discrete time slots of 20 minutes. There are local constraints of this problem that are related to the local vehicle capacity, local target state of charge at the end of the horizon, And there is a coupling constraint because there is a maximum power that the grid can deliver in each time slot. So we want to minimize what we pay for charging the overall fleet, and our decision variable is represented by charge, discharge, or do nothing. And when I charge and discharge, I do a certain rate. So if you look at the complexity of the problem, it's 3 because I have 3 options. To the power of 24, the time slot, and multiplied by 250 vehicles, so this number of possible combinations. But if you look at the local problem, it's much lower because each vehicle has 3 options over the 24 time slot. So you see that if you reduce from the global centralized optimization to a local one, you gain a lot, you gain feasibility in practice. So what we did is generating 100 instances of this problem by taking at random the value of a different coefficient involved. For every instance, according to the theory, we found a feasible solution, and we compared this new control-inspired approach to the one that was the better one than Bujanic, so the one of Falsone, in terms of reduction of the percentage of maximum component of the tightening and the normalized difference of the cost. And what we get is that the control-inspired approach has a normalized in percentage difference of the a normalized reduction of the constraint tightening, which is high. I don't know why it's so bad. So it works better. And this has an impact also on performance. The one of the adapted approach, it's worse than the one of the integral-based approach. Then recently we are working also on this other problem. We thought that since we have a powerful technique for decomposing and solving multi-agent mill problem, why not considering starting from a large size MLP with a sparse constraint matrix, the possibility of converting it and decoupling it fictitiously in a multi-agent MLP. And this means that the matrix, A tilde, that I showed you before, should be by shifting the rows and the columns, reduced to a form which is a block diagonal with a border. So the border would represent the coupling constraint, and this diagonal block the local constraint. And we started playing around with different possible approaches. This was one that was developed by Lucrezia Manieri together with us, by in hypergraph representation of the constraint matrix, where columns are nodes and instead rows are nets, and we try to find the cut that minimizes the number of nets so as to have a few little global constraints. But recently we have been extended using another approach which interprets the matrix A as converted in the probability characterizing the evolution of a Markov chain associated with the graph representation of a matrix to do the same thing, try to decomposition. So I came to the end of the summary. So what I try to illustrate is our framework for multi-agent system performance optimization. We try to take into account different aspects of different dimensionality of complexity, large scale, the need of privacy, the heterogeneity of the agent, uncertainty affecting the problem, combinatorial complexity. We applied it to a number of possible energy-related examples. Energy management of a building district, I show you plug-in electric vehicle charging schedule, but we also work out some interesting results, which I didn't have time to show you, on the aggregation of prosumer for providing balancing services to the grid in this paper. And what really struggles us is proving convergence rate, try to figure out we know that it converges, but what's the rate? We have been working out more recently distributed approach where the CK is converted to be a constant to avoid this slow convergence, and it worked effectively, but I didn't have time to show you also this result. And then what about the MPC implementation? What about addressing uncertainty in the constraint coupled MIP problem, where the scenario theory is not applicable because we are able just to compute a feasible but not the optimal solution. We have some preliminary results based on statistical learning theory, but they are really conservative, so in practice ineffective because you need an enormous number of samples, and we like also to address more applications. So this work wouldn't have been possible if just in alphabetic order, without the help of Alessandro Fassone. As you saw, it's the first author of many of our papers. So he was my PhD student and now is my colleague. Simone Garatti, especially for the uncertainty part. Lucrezia Manieri, who just finished her PhD. And then Kostas Margelos, who since a few years back joined with success the University of Oxford. And we had some support from EU through different projects. And this, thank you and hope to see you in Milano.
We have time for some questions. Do we have any questions?
Yeah. Hiya. Thank you very much for the talk. It was really interesting. I was wondering, for the car charging example, you set 3 states: charging, discharging, nothing.
Yeah.
Why is discharging considered at all? I know it's very specific to the example and much less to the broader theory. I'm just curious, because that adds a lot of cases. Yeah, sorry.
No, sorry. You were asking why is
So you set us 3 possible states,
yeah.
But one of the states seems to be kind of superfluous, like allowing the car to discharge at all just gives you more work later.
Yeah, in principle, I mean, if the cost, the grid does like that, the cost which is different per time slot. So it could be convenient for you to sell and then...
Oh, okay. I then factored in cost. Okay, that makes sense.
Yeah.
Thank you.
Thank you. Do we have any other questions? If I may ask, we have one here? Peter.
So, it's possibly quite naive. In the beginning, you said you don't need the gradient. Is this due to your sampling, or?
Okay, I don't need the gradient in the sense that the basic step doesn't involve the gradient, but then you have to solve the optimization problem. So for some cost function, it could be easy, closed form, or you might need the gradient to solve the problem. But then you use that solution, which is regularized by the quadratic cost, so it's better performing than the other one.
Okay.
Any other questions? Can I ask you one?
Yeah, sure.
You had the example where you had a building with 3 levels, and then I assume you had other buildings as well.
Yeah.
Could you set it up where you have a hierarchy, so you have more than one layer of agent?
Yeah, you could treat them separately.
Yeah.
Yeah, this is what did I understand?
Yes.
Yeah. It's just a matter of. I mean, in principle, every zone could be an agent.
And would that then change the dynamics, or would it end up being the same problem?
You'd have, if you model, if you are not isolated, you'd have some coupling, which added on top of which would add on top of a problem. So you have to look into the specific structure and possibly move from a decision coupled to a constraint coupled problem, seeing its decision variable as belonging to each agent and the coupling created by the constraint, because they exchange through the floor, the ceiling, they are not isolated anymore. So if I choose my set point, I'm affecting your dynamic. So you have to look and write the equations and figure out what's the most convenient formulation. Yeah.
Thank you. Okay, so can we thank Maria again for an excellent talk?